Hello, today we're going to present the topic of buffers and the Henderson-Hasselbalch equation. Okay, look, here's the thing. Jenny, your chemistry teacher, gave you a set of questions about buffers. Now, you don't want to disappoint Professor Jenny, and you decided to answer the questionnaire. Now, the thing is, you don't know how to answer this question. First and foremost, we have to do a refresher course on certain topics. Disclaimer: We will, we will be showing a quick and simple refresher concepts relevant to questions in the questionnaire, provided by Professor Jenny. If you want to learn more about some of these topics, we will link some other videos provided by our collaborators on those specific concepts. For our first concept, we shall discuss acids and bases. Now, acids and bases are one of the most common concepts that you must be aware of, as the whole idea of buffers rely on those two terms, and how they relate to each other's work. To determine whether a substance is an acid or a base, simply count the hydrogens on each substance before and after the reaction. If the number of hydrogens has decreased, that substance is the acid, and if it has increased, the substance is the base. For our second concept, we have the common ion effect. The operation of a buffer system depends on the common ion effect, a special case of Le Chatelier's principle. To keep everything clean and cut, when a solution of weak electrolyte is altered by adding one of its from another source, the ionization of the weak electrolyte is suppressed. In certain situations, where the given concentrations of acids and bases are not absolute and can be altered, the effect of the common ion influences the magnitude of the concentration. And now, on to our main lesson, the buffers and the Henderson-Hasselbalch equation. Now that we have some of the more relevant concepts down, let's begin. A buffer solution contains a conjugate acid-base pair with both the acid and base in reasonable concentrations. The conjugate acid-base pair must be of weak to moderate strength. Strong acids and strong bases do not make buffer solutions. An acidic component with added strong bases. The basic component reacts with strong bases. The basic component reacts with strong acids, and here are a list of some of the strong acids and bases for reference sake. The reason for this is that the solution of a strong acid and its salt has the acid nearly completely ionized, so the strong acid cannot be present in significant amounts. The same goes for bases. Basically, it means if either the acid or a base is too strong, it can dominate the solution, displacing its conjugate pair. So please keep that in mind. Now we have an example of the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is pH is equal to pKa plus the logarithm of a conjugate base over its acid. The value for pKa will be calculated from a value with a negative logarithm function. Here's a simple solution from the problem from the last slide. Now, we shall answer the questionnaire given by Professor Jenny. Question 1. You prepare a buffer solution by dissolving 2 grams each of benzoic acid and sodium benzoate in 250 ml of water. What is the pH of this buffer? Assume that the solution's volume is 750 milliliters and the Ka of benzoic acid is 6.3 times 10 to the negative 50.
To reiterate, we have 2 grams of benzoic acid. The molar mass of benzoic acid is 122.123 grams per mole. And we are given the volume of 0.75 liters. The same with sodium benzoate. We also have 2 grams of it. The molar mass is different from the benzoic acid. It's 144.105 and the volume stays the same. Now, we also have Ka is 6.3 times 10 to the negative 5. Now, given this, we have to plug this all in the Henderson Hasselbalch equation. But the problem is, these given by itself cannot supply the Henderson Hasselbalch equation. The only thing that we can do now is derive the given, the base, the acid, and the pKa from the given values. Okay, first you have to find the molarity of the base and the acid. We're going to be using this equation. Molarity is equal to grams over the molar mass over the liter. Since we're given this already, the only thing that we have to do now is plug it in the equation. Now, for benzoic acid, M is equal to 2G over 122.123 grams per mole divided by 0.75 liters. Now, I advise you take out your calculators and solve with me. You can pause the video anytime you want, just to check if your answer is correct. Now, this is the answer. The molarity of benzoic acid is 0.0218359081. Now, if your scientific calculator has a function to store the answers that you've got, please try and store it with A. But for the other people that are solving without a function like that, A simply means the molarity of benzoic acid. Writing this will be a hassle, so we're going to use letters to represent their values now that we've found their values. Now, the same goes with sodium benzoate. The molarity is equal to 2 grams divided by 144.105 grams per mole divided by 0.75 liters. Now, you may pause the video and solve it yourself. Now, this is the answer. Molarity is equal to 0.01850502527, which will be represented by B for simplicity's sake. Now, you have to find pKa. Now, to get pKa, we have to get the value of Ka, which is 6.3 times 10 to the negative 5, and plug it in negative log. Now, once you put the value inside of negative log, the answer is now 4.2006599451, which will now be denounced by C. Now, you have to remember always that Ka is not equal to pKa. You have to put it inside negative logs for it to become pKa or pKb. Depends on the equation and depends what's being asked. Now that we have the molarity of the base, the acid, and the pKa value, the only thing that you have to do now is step 3, which is to plug in the values inside the Henderson-Hasselbalch equation. Now, bring out your calculators. Well, I assume that you already have them out. Now, solve for pH. I'll pause the video just to solve the pH. Now, I assume you already have your answers. Now, what's the value for the pH? For simplicity's sake, this is the answer. The pH can be 4.129 or 4.13 for those decimal freaks outside. Now, that is how you're gonna get the pH given these values. This is the whole solution for the first example. Thank you.
Holy power. From the pH of a solution that is 9.0 molarity in NH3 and 0.80 molarity in NH4Cl, and find the pH of the solution after 0.10 moles of HCl has been added to 1 liter of the solution. As said in the equation, NH3 has a concentration of 0.9 molarity and there's a concentration of 0.8 molarity for NH4Cl. The Kb of NH3 is equal to 1.8 times 10 to the negative 5. Now, we use all of this data to find the pH. First, we use the Henderson-Hasselbalch equation for bases. We compute for pKb, then here, with the base and its conjugate acid, we compute. The final pOH is 4.693874972. Now, we will input that into letter A. To find the pH, we subtract letter A from 14. This is the final pH. But now, we add 0.1 molarity of HCl, and we find the pH. Here, we arrange the table with the reactants and its product. Then we form an ICF table. We place the initial concentrations, and here, we make sure that HCl is erased from the equation by making it 0. So we subtract 0.1 from both compounds on the reactant side, and add 0.1 to the product side. Here, it results in 0.8 for NH3, and NH4Cl has a concentration of 0.9. We repeat what we did on this side and use the Henderson-Hasselbalch equation for bases. We compute for pKb, and like on the other side, we use the base in its conjugate acids concentrations to compute. The final pOH is 4.795880017, which we now input into letter B. Again, we subtract it from 14 to get the pH. The final pH is 9.204 or rounded off 9.2. That's the final pH. Thank you. Congratulations for completing the course.